Thank you. So, hello everybody. What a better way to finish the day with some deep academic AI, but okay. So the talk is indeed called Adapting Like Humans, Embodied AI Beyond Dataset and Domains. And of course, before delving into tech, this has been not just my work, it's a work of a large group. So I've been with Theo, Mark, Linus, Joao, also 4 professors are with us, Matteo, Hossein, Hedvig, and Daniel. Of course, all of us, we're all coming from many different institutions, both academic and industry. And our work has been published in ICCV and DCCV in the last 2 years. Okay, so let's start with some bold statement here. We have reached a state of superhuman perception. So these slides come actually, it's a screenshot from Tesla AI Day of a few years ago, and already there we could see marvelous things when it comes to perception and robotics. Like we can see so far very small cars and pedestrians. We can measure the distance perfectly. Like really, we have so many sensors. Therefore, autonomous driving must be a solved problem, right? Well, not really. Or it's a solved problem until the unexpected happens. So here we see classic task for semantic segmentation. Semantic segmentation, for the one of you which are maybe not from computer vision, effectively means to give a classification for each pixel in the image, saying like this is a car, this is a road, this is a sky. And then we just have a tiny bit of rain on top of this image. And we see the classification, like the segmentation falls apart. This is a Pollock, it's not segmentation anymore. What we call here in AI, what's happening here, it's called domain shift. So we have a shift between the deployment domain and the source domain, the training domain. We call the training domain the source domain, and what we instead deploy, the target domain, where we want to be great at. And the problem is that the unexpected happens all the time. So how do we solve this? So there are many. I identified here 3 correct answers. So there is one that you are all thinking about, and is this one. Just add data. I mean, what else can you need? There's a problem. It's really slow. It takes so much time to collect this data, to annotate this data. It's a big process. Like we've seen the presentation from Mina from Densect. She can tell you how much it took to create a data set. And it's also very expensive. Not just to collect data, but also to annotate it, especially if you want to annotate it using ethical workforce. It's really expensive. And this is also exacerbated in many ways by, for example, the long tail problem. That most of your data, you already have them, and you're going to get more and more of what you already know. But then you have a very long and fat tail of things that are really rare, but they're extremely difficult to catch. Another problem is the cost of dimensionality, that domains are combining one each other. Let's say weather, and then urban and rural scenarios, like they're combining. So you have all the combinations of this. As you increase the number of domains, the number of combination explodes. And finally, is that data is not forever. Like you collect some data today, you think, it's going to be with me forever. No, there is an expiration date on that data, like task changes, sensor changing, like everything changes. So another option could be, okay, you know what? I'm going to generalize. So here is an example of domain generalization. That means like data augmentation. I'm going to create variation, break some biases, and hopefully everything will work out. There is a problem that you don't know which biases you're breaking. And some other biases, you don't want to break them. And who is deciding which bias to break? It's get iffy. It has limited impact, and we see it. It's useful, we all do it, but, well, it doesn't solve the situation. And then there's another issue, like, is it even possible to prepare for the unknown? Like, we don't know where we're going to deploy. Like, how can we generalize to everything? So then we can take one step back and think, how are humans solving this? Well, we don't need any limited amount of data, and we don't augment our data, but we adapt. So we're not hardwired. We rewire our brain constantly. We train, we understand, okay, we're not that great at that, let me study a bit more. I'm not that great at this, okay, let's collect some more data here, try to understand what's going on. Can network do the same? And this is also the embodiment part of this presentation. So there is one field in AI called unsupervised domain adaptation, which came, let's say, became quite popular thanks to simulation environments. It's quite easy, as the simulation environments are getting better, it's quite easy to use them to collect data, cheaper than going out in the street, and also to annotate this stuff, because the annotation comes for free. I need to change a task. I can just change the simulation environment. I don't need to re-annotate all the data. And these annotations are perfect. And there is a problem that when we train on the simulation data, then we want to deploy in reality, not in simulation, of course. And there we will find our domain shift that will break everything apart. So what can we do? We can take a bunch of data from real data, so collected, but no labels, and then we teach to the AI a way to transition from what has been learned in the simulation environment to the real environment. And this can be done without any labels. Good, but there's still a catch. So here we still assume that we know where we're going to deploy. But this is not the case for most of the system. If we imagine embodied system, if we imagine system that will run and will live together with us, they don't know where they're going to be deployed. And this is the point. Domain change unpredictably. We don't know what's going to be the next domain shift. So this brings us to the first publication that we had, which is indeed called Online Domain Adaptation, in this case for semantic segmentation in never-changing conditions. So first of all, we realized that we needed a benchmark. This benchmark we created taking a very popular autonomous driving dataset, which is cityscapes. We added rain, like a bit more and more and more and more. So we adjusted a few millimeters and then more and more. And we are not just adding rain on top of it, it's synthetic rain, but we also darkening the sky and doing a lot of other visibility effects to make it more realistic. And then out of it, we create this kind of, we create a storm. So we start from a bit of rain, and then we propose the same data set in a different, shuffled in a different way with a bit more rain, and et cetera, et cetera. And then, crucially, we start from 0, and we come back to 0. So we can also measure if during the process we can adapt, but also if we forget where we come from. So we forget source, the sunny scenario. So let's start to put some baseline first. Here we have just a segmentation model trained on source, our training set, and then we tested on target. And well, actually here we can see how the performances are going basically linearly down with as we increase the millimeters of rain. So what if we just apply traditional unsupervised domain adaptation? So we take all the rainy data, we adapt to them before the deployment, and then we deploy. So in this case, the model is better because, of course, it has seen rain, not the labels, but still, it has been adapted on that. And to do this, we use this student-teacher setup that you can see here. But now, what if we instead adapt the model step by step? So in this case, to simulate a real deployment scenario, we don't use all the labels, but we only use this buffer of training data, and then we adapt it very slowly. And here you can see that it's better. We don't forget, which is good, but still, we are still losing quite a lot in the hardest domain. So another option is instead, what if we now embed some form of domain observer within our network, which can identify when a domain change occurs. We identify that, and then when we identify the domain change occurs, we change the teacher student, the teacher model, and we use this current student. The current student becomes a teacher, and then so the teacher somehow get updated and get a teacher which is likely to be better in the domain that we're going to see. And here we see that we get even better, but there's a problem that we forget. So once we basically we have the storm, imagine it starts to rain, then it stops to rain, slowly fades out, but then the model at the end is not as good as it was. So that's what we realize is that we need to orchestrate teachers. It's not enough to just have one, we need to have multiple. And every time, according to what's happening, in what is the domain that we are going to face, we pick the one that is the best for us, using some form of orchestration that I'm not going to delve into that now. Okay, how can I do this? That's a video, okay. So here you can see effectively what happens in the hardest domain. So here you have the video footage, of course, on the top left, and then you see the source train model, which is no adaptation whatsoever, and I mean, hard to say what's going on there. We have offline adaptation, which is the state of art of online adaptation in 2022, and then our online adaptation model instead, that is adapting as images comes. And of course, the improvement is really significant. Still, we see some problem, but I mean, it's not a pollock. Okay, there's another thing though. Sure, now we can handle domain changes, which happens unpredictably, but we're not fast. We know that if we wanted to have it really in cars or any other robot or any other system, this should happen in a timely manner. And this brings us to the second work that I'm going to talk about, is to adapt or not to adapt, real-time adaptation in semantic segmentation. So here we keep the same structure, including one student and two teachers, one static teacher and one dynamic teacher. And in this case, we don't focus so much on the teacher orchestration, but we focus on other three questions. So the first question is, what do we need to adapt in the model? Is it always necessary to adapt a really big neural network all the time? This sounds extremely expensive. We have a lot of parameters to train. And the answer is, of course, no. We don't need to change all of it. So what we create is a decision, basically a reward-punishment algorithm, which effectively runs online a cost-benefit analysis between what is the time the time that it takes to train a specific segment of the network, and the expected benefit of training that expected network. And then we juggle this algorithm decides every time whether it's necessary to train all the network or a larger part of the network, or instead train a tiny bit. And of course, training a tiny bit is way more convenient than training the whole of it, but sometimes it might not be sufficient. The second question, and actually also the third one, is that when and how to adapt. Because we don't have domain changes all the time. We have them once in a while. So if we could understand when the domain shift happens, then we can only trigger the adaptation process in that specific moment. And that's not all. If we can also understand how big is the domain shift, and whether this is going, let's say, in a even more unknown territory in some sense, or instead it's coming back towards what we know already, then we can understand somehow how much we need to adapt. So do we need to adapt for a long time, for a short time, and we can effectively tune the training parameters according to the domain shift that we are experiencing. And we can see that it's working pretty well. So here we have both on the left, all the domains. So like we average all our results over domains, and on the right instead, we see only the hardest domain. So we both compare against other adaptation methods, then we either force them to run online, either with our speed or at their speed, but of course it's going to be very slow. And we see that we beat both cases, but you even try because someone could say, okay, sure, you have all this complicated architecture to train stuff online, but what if I just take a way larger network, and then I just rely on that, and I rely on the power of generalization. But then here we see, and this happens here, for example. So you see that when we take all the models, we can take this segformer MIT B5, which is the largest, and it's a bit slower than us, but it's a bit better. But then if you take the hardest domain, I mean, it doesn't really matter how big you are. You're still not going to work if you haven't trained on that domain. So here we see a video, which is actually a YouTube video. So so you can imagine this has been a model trained on cityscapes. Never seen this camera before. Never seen Korea or highway or rain or night. And you can see the effect here in the non-adaptation. It's really bad. But then you see our model, which is actually called Hamlet. You haven't said it before. And you can see that, surprisingly, it works, or it works better. And actually, it works good enough that companies are already thinking about integrating it in a real product. And so who could think about something like that? And so I don't know if you've read this article or some others. So it says like OpenAI agreed to buy 51 million of AI chips from a startup backed by CEO Sam Altman. So it's a document shows that OpenAI signed a letter of intent to spend 51 million on a brain-inspired chip developer, startup Brain. Sounds interesting. We're also doing stuff somewhat human-inspired. And indeed, Brain AI is this really innovative startup in San Francisco, founding on basically two principles. The first one is neuromorphing computing. In particular, they work on DIMC, which means digital in-memory computing. So this is a really cool way of doing computing in-memory computing, because it means that the computation happens in the storage, effectively. So there is no data transition between GPU and storage. And of course, if you want to train online, you need a loss function. That's kind of the twist. And they're using Hamlet. So we wish them good luck. So what's next? So first of all, is Hamlet safe? No, not yet. Why? Because there are no guardrails. So we haven't experienced, we haven't measured somehow any catastrophic forgetting, but we know it might be possible. We introduced some regularization practices, but there's no mathematical guarantee that this will not happen. So can online adaptation be safer and, crucially, explainable? And the second question is, can we instead focus on the data? So now data generation always requires a lot of sequences. Can we instead reconstruct a scene from a single view and maybe even edit it a bit with a textual prompt? So this is what we're working on now, and this is actually a project that we are working in Silo AI, so thank you. Anyway, so training free and explainable adaptation. This is the first one. Here we actually got inspired a bit by this mixture of expert models that are so trendy in the language area. Can we do something similar in the vision area? So the idea here is that we're going to rely on a library of LoRa's. If you don't know, LoRa's are this kind of form of plugins that we're gonna that can be plugged into a model and improve the performance of the model in that specific area. And LoRa's also have this nice property that can be combined. So if we see a domain, then we can say like we can create an embedding of this domain, understanding which LoRa's should be combined and how to combine them, and then replug this LoRa into the model. And another thing that I said before is like, can we generate a view, a whole scene just starting from a single view? So we take RGB and LiDAR, we apply some scene completion, we generate Gaussian splats for that. Like we sample, hopefully actively, from this Gaussian splatting, and then we pass it through stable diffusion. We apply SDS loss, that is something like, I don't remember, but score distillation sampling loss, and then we effectively denoise the Gaussian splats. And that's all. Thank you.
Pier, thank you so much for that contribution. We're actually going to see if there's like one question in the room, and then we're going to go and switch to the bigger room where we started off today to finish today. But before that, let's see if there's a question here. Yeah, if there's no questions, we're going to have, we have 10 minutes. Oh, yes, please. Let's you get your microphone as well.
Yeah, so I was wondering, maybe you mentioned it, but I missed it. But when you're doing this adaptation in real time or online, let's say you're in a new deployed model and it's in a new environment that you're trying to adapt to. Where does the ground truth come from that you would be using to fine-tune or adapt the model? Or was that somehow part of this architecture that you showed?
Yeah, the thing is like we don't have any ground truth because, of course, we are adapting to this new domain. There is no ground truth, especially online. So the ground truth is somewhat a pseudo label. It's not a label, and it's provided by a teacher model. So effectively, we have a teacher model, which is a model which is regularized and should be stable. It doesn't need to. It's always. It's not better than the student, but should be less. Should be more stable than the student somewhat. And then this prediction of this teacher model is then feedback to the student model, and the student model is supervised with effectively an EMA version, like exponential moving average of itself.
Great. Let's continue on right here. Yeah.
Sorry, my question kind of follows on from that, but does the teacher model then not need the original data volume? Like, you said you've got lots of vehicles driving, and now you need some rain. Does the teacher model not need that data that you could have trained the actual model on? Or
so the teacher model and the model itself usually are pre-trained on the source model, on the source data set. And then we take the teacher model. The teacher model gives a prediction. Usually, but not always, we only select the high confidence range of this prediction because we assume that, and this is an assumption that actually holds, that supervised training models are usually quite well calibrated, better than self-supervised models. So we take the high confidence prediction of the teacher model, and then we feedback to the student model. So the student model in this case will receive prediction from the teacher model which are like reliable. And then usually we juggle with multiple teachers. So we have one teacher which is not training at all, it's gonna be frozen in time so that we avoid catastrophic forgetting, and another teacher which instead adapts together with the student so it can provide more updated prediction. Otherwise the student saturates at some point. I don't know if I answered the question.
yeah, that's fascinating.
Okay.
Great. Was there another? Let's take one last question. Let's go right here. Yeah.
Okay. I kind of have like two questions. First is that do you adapt to one domain at a time? For example, like if you adapt to rain, should I train again for adapting to night or winter or something?
So we always adapt to basically the current domain. So we don't adapt like the model. We try to simulate a realistic scenario. So you only adapt to the domain that you are basically facing at that specific moment. But then we also notice that by training, like for example, if I now see a light rain, very light, and then I start to adapt that adaptation of on this light rain, I'm actually, even if I don't know it yet, I'm actually getting so much better in handling heavy rain already, even if I've never seen heavy rain, but just by the act of adapting on this progressive, easy domain, which is like light rain, give me so much benefits. It's kind of a propedeutic task. Like I do something simple and I automatically get so much better when I will need to do something way more complicated.
Yeah, and the other question is that do you have kind of a neat definition for a domain, or what do you mean by a domain?
Yeah, no, it's a good point. I haven't covered on that. So the domain is effectively a data distribution. So it doesn't only cover the let's say RGB part of the data, so the raw data, but it also covers the distribution of the labels. But if you take a data as, let's say, a data distribution as a joint probability between, data and their associated labels, then a domain represents one distribution of data. So if you have, indeed, the first ways of measuring domain shift that are not doable anymore, but when there were very few dimensions, like back in the days, you can do with a KL divergence, because effectively you can measure it as a distance between these distribution. But now, of course, we work with images, that are impractical distribution. We cannot too many dimensions, so Now you can only measure an empiric, like you can have an empiric, how can I say, yes, just a proxy of the domain shift. It's a more, you don't measure it anymore.
Great. I realize there might be some more questions in the room, but maybe you will be available for some questions after the session.
Of course.
Pier, it has been our pleasure to have you here. Thank you so much for your contribution.
Thank you.